Hello, everyone. My name is Abdallah Makhoul. I am a professor at the University of Franche-Comté in France. Today, I will present our invited paper to MENACOM 2021, entitled A Multivariate Data Reduction Approach for Wireless Sensor Networks. So here is the outline of my presentation. First, I'll give you an introduction, brief introduction about wireless sensor networks and different data collection models in sensor networks. Then I will define what we mean by multivariate data reduction. I present our technique of in-network data processing for heterogeneous wireless sensor networks and multivariate data reduction techniques. I will show you also our obtained results, and I will end my presentation with conclusions and some perspectives. First of all, as you know, all of you, wireless sensor network is a network composed of low power and low computational sensor nodes, several thousands of sensor nodes in a defined area, which we call it area of interest, in order to monitor it, to collect data and transmit it to the end user. Data collection from sensor networks can be made by two ways, on demand or by data streaming. The first category is done by bidirectional dialogues between the sensor nodes and the base station. A request for data is sent from the end user via sync to the sensor nodes, which in return send back the data to the user via multi-hop communications. But on the other side, in data streaming, data flows primarily from the sensor node to the sink. In this category, we distinguish the periodic sampling and the event-driven data models. So in our approach, or in this work, we are interested in periodic sampling data model in sensor networks, where the acquisition of sensor data from a number of remote sensor nodes are forwarded to the gateway on a periodic basis, as we show here in the example. During a period, each sensor collects 2 readings, and each period is divided into slots. At each slot, each sensor collects 1 reading. So, based on the application purposes of wireless sensor networks, sensor data can be categorized into univariate and multivariate data models. Univariate data represents a sample of one feature or one phenomenon feature, for example, temperature, when say a sensor node just collect one feature, like temperature. Whereas multivariate data represent different features, like humidity, light, etc. And nowadays, sensor nodes are equipped with different types of sensors that provide the ability to monitor different phenomena features by one sensor node. For example, temperature, humidity, light, voltage, etc. So it's clear that here in this kind of models, or data model, multivariate data model, the transmission of multivariate data from one sensor node will increase the power consumption because of the high radio communication cost. And one effective technique to save energy is data aggregation. So in this work, our focus is on saving energy by reducing the size of the transmitted data, the multivariate transmitted data from the sensor nodes to the sink. So the data aggregation, as defined in some previous work, is the process of minimizing the data packets coming from different sources. And the majority of existing approach focus focus on univariate data reduction techniques. And these approaches are applied on a set of observations composed of one feature. Here in our approach, we will consider multivariate data reduction, and we propose a data reduction techniques based on polynomial regression and Euclidean distance techniques. So here is our data structure. We considered a network composed of little n nodes, and big N is the set of all the nodes. Each node is equipped of a set of sensors Sy, the set Sy, and K is the number of sensors to collect measurements related to different features or different fields. And in periodic wireless sensor network, at each period is divided into slots, and at each slot, each sensor collects one measurement, and one sensor node collects K measurements at each slot. So after each period, we have each sensor node has a matrix composed of several vectors. Each vector corresponds to one slot. So at each slot, a sensor collects one vector, one of K measures, and each measure corresponds to one feature. For example, this for temperature, this for humidity, for voltage, etc. So the idea here is to reduce the size of this matrix before sending it to the sink in order to save or reduce the energy consumption. So our approach is divided to two phases. The first phase is the aggregation phase. And here the objective is to reduce, if you want, the number of lines in this matrix, to study the similarity between these lines and eliminate redundancies in the lines of the matrix. For this reason, we propose to use the Euclidean distance and find all similar vectors in this matrix according to this equation. And based on a threshold that can be defined based on the application. And we define also a vector frequency. The similarity is calculated only with consecutive vectors. If two consecutive vectors are similar, we eliminate one and we increment the frequency of the first. As we here, I'll show you an example of temperature, humidity, light, voltage. Here is the matrix. If we calculate the similarity between the two vectors here, we obtain the Euclidean distance equals 0.01. What if the threshold is 0.05? So we consider that M1 and M2 are similar, and M2 is omitted, and the frequency of M1 is incremented by 1 to say that we have two vectors with high similarities. And when the matrix is sent to the sink. The second phase is the data correlation. So here the goal is to take into account the existing correlation between the features. We can find spatial correlation, temporal, and spatial temporal correlation. So first we studied the similarity between lines, between the vectors. The idea now is to study the correlation between the features collected by one sensor, is to use linear regression and fitting function in order to find the correlation between the feature. For example, the correlation between temperature and the humidity. And instead of sensing all the columns, we send one column and one function in order to reconstruct all the matrix at the sink level. So further reduction of the amount of data transmitted from sensor nodes to the aggregator using a polynomial regression and the fitting function. So here is our matrix, our reduced matrix. First, we reduce the number of lines here by aggregation. We study the similarity between these vectors and then the correlation between the features. If we find a correlation between X and Y, we send only the X, the column X, with the fitting function to the sink in order to reconstruct the other columns at the sink level. And by doing this, we reduce the amount of data transmitted from the sensor to the sink, and we reduce the energy consumption. So to validate our technique, our proposed technique, an R-based simulator is implemented, and it is run on real data collected from 54 sensors deployed in the Intel Berkeley Research Lab. So we considered 10 nodes were chosen to simulate local aggregation step, and it was assumed that the network contains one aggregator located at the center of the lab and a set of sensors that periodically send their data to the aggregator. The goal is to demonstrate that this technique can successfully achieve desirable result in decreasing the power consumption of heterogeneous wireless sensor networks or multivariate data model. So simulation, our simulation, several metrics were evaluated: the percentage of data aggregation, percentage of data reduction, the accuracy, and the energy consumption. So in the first results, I will show you the results of the aggregation phase. So in this simulation, we varied the threshold of the Euclidean distance between 0, 0, 1 and 0, 1. So it depends on the collected measures. And tau between the number of slots in each period between 20 and 100. So here in this figure, I'll show you the percentage of the remaining measures at each period with and without aggregation at each sensor. The obtained results, as you see here in this figure, the obtained results show that our method can, in the worst case or in the worst scenario, reduce up to 86% during the aggregation phase. Therefore, our technique can successfully eliminate redundant measures at each period and reduce the amount of data sent to the aggregator. And here in the second phase, we use the polynomial regression. And in this table, we show you the correlation between temperature, humidity, light, and voltage. So when the correlation is near to 1 or -1, we mean there is a lot, that the correlation is high. And we find that the temperature, the feature temperature has correlation with humidity, high correlation with humidity. So here, we test the accuracy of our method, and it can be clearly seen here by comparing these two curves or these two curves that there's not big difference between the plot of the estimated variables at the sink level and the original data. So here is the original, and here is the data reconstructed at the sink level. Also, this table here shows good results after estimation for the coefficient of the determination R-square, which is a statistical measure of the closeness of the data to the fitted regression line. The higher the R-square value, the better the fit. Also, the root mean square error is calculated. It's a measure of the quality of an estimator. So values closer to 0 are the best. So to conclude, in this paper or in this work, we propose two-layer data reduction techniques to save energy in multivariate wireless sensor networks at the node level. First, each sensor aggregates captured measures based on the Euclidean distance. Second, the high correlated parameters are fitted so that the estimated coefficients representing the values of the slope calculated by the regression are obtained. The omitted parameters during the regression phase are recomputed and reconstructed at the sink level using the fitting function and its coefficient values. The efficiency of our approach in terms of data reduction and energy consumption is shown through simulations on real data measurements. So thank you for listening. And if you have any questions, do not hesitate to contact the authors of this paper. Thank you.